In this video, we will look at some advanced transformation techniques. They are different from the basic transformations which we have learned in the previous video, in the sense that these transformations will radically change the fundamental shapes of the graphs. The three types of advanced transformation graphs in the H2 syllabus include the modulus graph, y equals to mod of fx, and y equals to f of modulus of x. The reciprocal graphs, y equals to 1 over fx. And finally, the derivative graphs, y equals to f prime x. For each of them, there are multiple steps to take note of, unlike those in the basic transformations. We will now take a look at each of them in details. The first type of modulus graph involves putting a pair of modulus over the entire fx. In the mod fx graph, all positive y values remain invariant, but negative values of y becomes positive. Thus, the portion of the graph that is originally below the x-axis will be reflected and flipped to above the x-axis. The portions of graph originally above the x-axis remains untouched. So if I have a graph that looks like this, what happens is the portion that is originally below, it will be flipped upwards, whereas the part that is originally at the top will remain at the top. So we will end up with this graph like this. In example 1, we are asked to sketch the graph of y equals to mod fx given y equals to fx. So what we should do is to flip the portion that is originally below the x-axis upwards. Later on, we will delete the part that is originally below, and we will end up with the graph like this. Note also that the asymptotes should be flipped. The second type of modulus graph has a pair of modulus just over the x. In this case, points with negative x values will have the same y values as their corresponding positive values. For example, f of modulus of negative 2 will have the same value as f2. So the left side of the graph is actually going to be a reflection of the right hand side of the graph. Thus, when sketching this graph, we first delete the portion originally on the left of the y-axis. Thereafter, we will reflect the portion that is originally on the right hand side of the graph to the left. But we do not delete the portion that is originally on the right. So if we have a graph that looks like this, what we do is first, we delete away everything on the left hand side. Next, we reflect the remaining portion to the left hand side. And this remaining graph, like this, will be the graph of y equals to f mod x. In example 2, we will now practice how to sketch the graph of y equals to f mod x. Step 1, we delete everything on the left hand side. Step 2, we reflect everything that remains about the y-axis, keeping everything on the right hand side invariant. Thus, we end up with this graph for y equals to f mod x. We will now take a look at reciprocal graphs which take the form of y equals to 1 over fx. This transformation is slightly more complicated than the modulus graphs. To sketch the reciprocal graphs, we will need to identify the characteristic points, i.e. the points that we know their reciprocal values, and transform these points. Thereafter, we can join the transformed characteristic points to sketch the reciprocal graphs. The characteristic points that we should look out for in reciprocal graphs are: number 1, points close to 0, which graphically mean the x-axis intercepts. We know that when we take 1 divided by 0, it becomes undefined. So x-axis intercepts actually become vertical asymptotes. To the left and right of these intercepts, we have values which are very close to 0 but not 0. So these points will become either positive or negative infinity depending on whether they were originally positive or negative. For example, if I have a portion of a graph that looks like this, what happens is at the x-axis intercept, it is going to become a vertical asymptote. To the left of this point, we see that it was originally a very small value above 0. Therefore, it becomes positive infinity. So this point gets transformed over here. And the point on the right hand side of the intercept was originally negative, and therefore it gets transformed into negative infinity. So based on this single intersection point, we have three characteristic points that we can draw for our reciprocal graph. Here, here, and here. Number 2, the converse is also true. We want to look for points which were originally very large, since 1 over infinity becomes 0. So what this tells us is that vertical asymptotes will become x-axis intercepts, and points which originally extend to infinity when x becomes very large becomes horizontal asymptote at y equals to 0. For example, if I have this graph, that looks like this, it has vertical asymptotes here and here, and the graph probably looks something like this. It will be transformed into this point becomes 0, this point becomes 0, vertical asymptote becomes axial intercept, this point becomes 0, slightly larger than 0, and this point becomes slightly larger than 0 as well. So we have these characteristic points that are transformed based on the fact that it was originally of infinite values. Number 3, when we take reciprocals of non-zero constants, points which were originally larger than a constant will become slightly smaller than the reciprocal of the constant, and points which were originally smaller than the constant will become slightly larger than the reciprocal of the constant. For example, if I had a value of y equals to 2, and I look at y equals to 2.01 instead, 1 over 2.01 becomes 0.498. So we know that 2.01 was larger than 2, but 0.498 is actually slightly less than half. Horizontal asymptotes will thus remain as horizontal asymptotes, but they will have their positions shifted from y equals to k to y equals to 1 over k. Also, graphs originally just above the horizontal asymptotes will become slightly lower than the new horizontal asymptote, and graphs originally just below the horizontal asymptotes will become slightly above the new horizontal asymptotes. For example, I can have a horizontal asymptote over here, and this is my original graph. How it will transform is, first, maybe the new horizontal asymptote becomes here, and originally this was slightly above the horizontal asymptote. Now it is going to be transformed into a point that is slightly below the horizontal asymptote. Lastly, the natures of the turning points will be switched. Maximum points will become minimum points, and minimum points will become maximum points at their respective new y values. As a summary, these are the characteristic points for us to look out for when sketching reciprocal graphs. In sketching reciprocal graphs, it is good practice to start from the leftmost point and scan from left to right for the characteristic points which we have covered earlier, and mark out the points that they will be transformed into. Once the points are marked out, we can easily sketch the transformed curves. For example 3, we can mark out the characteristic points as such. First, this horizontal asymptote has a value of y equals to 3 over 2. Therefore, that means that our new asymptote is going to be y equals to 2/3. So it's somewhere over here. Next, this point over here is slightly larger than our horizontal asymptote. Therefore, it is going to be transformed into slightly lesser than the new asymptote. Next, as we move from left to right, the next characteristic point that we can find will be this point over here. It is at positive infinity, which means it is going to become 0, 0 plus. So somewhere over here. Vertical asymptote over here becomes axial intercept. Negative infinity over here becomes 0 minus. Next, we have an axial intercept over here, which becomes a vertical asymptote. To the left of the asymptote, it was originally below the x-axis. That means it is a negative value, which becomes negative infinity. So somewhere over here. To the right, it becomes positive infinity. Next, we have a maximum point over here, which means it is going to become a minimum point, maybe somewhere over here. Next, I have an axial intercept over here, which means it's going to become a vertical intercept. And to the left of the vertical intercept, it becomes a positive infinity point. To the right, it becomes a negative infinity point. Next, we have this vertical asymptote, which becomes an axial intercept. To the left of this axial intercept, it is 0 minus. To the right, it is 0 plus. And finally, if we look at this end point over here, it was originally above the horizontal asymptote. So now it becomes lower than the horizontal asymptote. With these points sketched out, we can easily join the dots to get a graph, which is going to look something like this. The derivative graphs will adopt a similar approach as the reciprocal graphs. We will first identify another set of characteristic points, and in this case, points that we know for sure they are gradients, mark out the transform points, and sketch the transform curve based on these transform points. In derivative graphs, the characteristic points are number 1, horizontal asymptotes since their gradients are all 0. This means that all horizontal asymptotes will be transformed into another horizontal asymptote at y equals to 0. The portions of the graphs near the horizontal asymptotes will thus either become slightly larger or slightly lesser than 0. To determine their signs, we simply have to look at the sign of their immediate neighbors, since they will take the same sign and their immediate neighbors are steeper and thus easier for us to determine the signs of their gradients. For example, you can make use of this diagram to help you determine the sign. Here we can have these 4 types of curves in all the graphs that you will be going through, and we can focus on the part near the horizontal asymptote. So if we are looking at this point over here, we know that the gradient is going to be 0, but is it going to be slightly more than 0 or slightly less than 0? It is difficult for us to tell at this point itself. But if we look at his immediate neighbor, let's say a point over here, we can draw a tangent and see that this tangent is actually having a positive gradient. Therefore, I know that at this point, the gradient is going to be 0 plus. At this point, we can apply the same technique. We cannot tell for sure what is his gradient over here. We look at his neighbor, which has a negative tangent. Therefore, this point has a gradient of 0 minus, and this point will have 0 plus, and this point finally 0 minus again. Number 2, oblique asymptotes have constant gradients and thus will be transformed into horizontal asymptotes of y equals to a. where A is the gradient of the oblique asymptote. The portion of graphs near the oblique asymptotes can either be slightly larger or slightly smaller than the value of A. And we can determine whether they are larger or smaller than A using this diagram. So imagine I have these two oblique asymptotes like this. This has a gradient of m, whereas this has a gradient of minus m, where m is just a positive real number. And the types of curves that can be present will be this, this, and this. Now if I start from the top right hand corner and look at this point over here, I know that his gradient is going to be m, but is it slightly larger than m or slightly less than m? We can look at his neighbor over here, and his neighbor is obviously steeper than m, therefore I know that the gradient at this point is also going to be larger than m, and I have a m plus over here. Whereas for this point, I know that the gradient is going to be close to negative m, and the neighbor is going to be steeper than negative m, and therefore this becomes negative m minus. And this point becomes negative m plus. This point becomes m minus, m plus here, negative m minus here, negative m plus here. And finally, this point will be m minus. Number 3, the gradients of vertical asymptotes have infinite values. Thus, vertical asymptotes will remain unchanged. But for the graphs near the vertical asymptotes, the gradients can either be positive or negative infinity, and we have to determine their signs using the same diagram as for horizontal asymptotes, as we will discover now. If I have this same diagram, but now I am focused on the vertical components. This part of the graph will have infinite gradient, but it is sloping downwards as we can see from its neighbor. It will therefore be negative infinity gradient. This part of the graph, it will be positive infinity gradient since its neighbor is sloping upwards. This will give us negative infinity. This will give us positive infinity. Lastly, we know for sure that turning points or stationary points have zero gradients. Thus, all stationary points will become x-axis intercepts. For example, if I have the x-axis here and a minimum point here and a maximum point here, this point is going to be transformed into the x-axis intercept, and this point is also going to be transformed into the x-axis intercept. As a summary, these are the characteristic points to look out for when sketching derivative graphs. Let us now practice the sketching of derivative graphs using examples 3a and 3b. As with the approach for reciprocal graphs, we will scan from left to right for characteristic points. So this point over here is going to become 0 plus. This point is going to become positive infinity, therefore it remains at about the same point. This point over here, it is also going to become positive infinity. This point is a maximum point, so it becomes 0. This point is going to become negative infinity, so it remains over here. This point becomes negative infinity, so it's going to be transformed down here. And finally, this point, it has a negative gradient close to 0, so it is a 0 minus, and it has a point over here. And with this, we can join the dots together to form the final graph, which should look something like this. Or this. Likewise, in 3b, now we have a graph with oblique asymptote, but we can apply the same techniques. So scanning from the left to right, this point, it has a gradient of half. Therefore, it is going to become a horizontal asymptote of y equals to half. Let's say it is somewhere over here. And this point has a gradient of about half plus, correct? Because if we look at the neighbor is steeper than half. Therefore, this point should be larger than half. And we have a half plus somewhere over here. Next, this point becomes positive infinity. This point becomes positive infinity as well. This point becomes an axial intercept. This point becomes negative infinity. This point becomes negative infinity as well. This point becomes an axial intercept. And finally, this point, it becomes half minus. So it is somewhere over here. And with all these points, we can join them together again to form the new graph, which should look like this. Like this. And like this. Or this.